All right, thank you very much. Good morning, everybody. Yes, my name is Jonas Obrist. I'm originally from Switzerland, but I've lived in Japan for the last 6.5 years. And yeah, we've traveled all the way from there. My talk is titled Artisanal Async Adventures, and I'm terrible at coming up with talk titles, so let me spend the first few minutes of the talk explaining what I mean by that. So the artisanal part is that what I'm going to do is handcraft some code live in front of a live audience, and I don't think it gets much more artisanal than that. Async is the main focus of the talk, and I'm going to say the word async a whole lot, and so I should probably explain what I mean by that word. Async is short for asynchronous, and specifically I'm talking about asynchronous I/O, and more specifically asynchronous network I/O. And the adventure part is that I'm going to do live coding the whole talk. So things will probably go wrong at some point, but I think a room full of Python devs should be able to debug any problems we're going to have. I'm going to use PyCharm as my editor for those who are wondering, and it's all going to be Python 3.7, of course, and we are going to use nothing but the Python standard library, but we will not use the async module. Because the idea of this talk is we're going to implement our own async I/O, our own async event loop, with the goal that maybe you understand better of how this works and why this works and why this could be useful. Because async I/O, asynchronous networking, and all these things have a terrible reputation of being unbelievably difficult, impossible to comprehend for mere mortals. And I think that is just patently wrong. And I hope that over the next 30 or so minutes, I can prove to you that it's not that incredibly hard and that the core concepts are actually not too difficult to understand. So let's get started. And to get started, we need to have a problem first. Because I can't really do much without a problem that we need solving. And the problem that I have is I came up with an unbelievable algorithm that will surely change the world. And everybody on the planet will want to use that algorithm, so we need a way to expose that to the wider world. And the way you do that is you put it on the internet. So I came up with an amazing algorithm, and I want to expose this to the internet in a scalable and efficient way, so I don't lose too much money. So let's get started. I'm going to show you now my amazing algorithm, so please get ready. This is going to be amazing. One thing before I'm going to start, I'm going to use type hints a lot, because I feel like they help make the code more readable. If you don't understand them, just feel free to ignore them. So, the algorithm is a Python function, takes an integer, returns an integer. What we will do is we'll take the integer, and we will add 42 to it. This is my algorithm. Thank you, thank you, thank you. And as I said, I want to expose this to the internet, and the obvious solution would be like to make a Flask app, maybe a Django app, or use some other cool fancy framework and things. But the problem is HTTP has way too much overhead, because again, everybody will want to use this. So we need to have super high scale, super fast performance. So we're not going to use HTTP, we're going to go a level or 2 levels lower, and we're just going to use a normal socket server and deal with raw bytes and that kind of stuff. And so if you've never done this in Python before, here's a very short tutorial on how to write a socket server in Python. So we're going to have a server that will listen to an address. And because it's a server, it will never return, will run forever. And we will define the address as being a tuple of a string, which is the interface to bind to, and an integer, which is the port to listen on. To make a socket server in Python, you will need the socket module. And I'm going to use some PyCharm magic throughout the talk, so it's just automatically importing things for me to make my life easier. And to make a socket, we need to tell it what kind of socket we want, and we say we want a address family internet and sock stream type socket. That just means TCP/IP, as in the normal thing you would expect. And we will also tell it to reuse its address if it can. That just makes it easier that if I restart the server all the time, that we won't get any funny ports in use problems. And then if you have a socket object in Python and you want to make it a server as opposed to a client, You have to bind it to an address. Again, that's a tuple of interface port. And then you have to tell it to listen for incoming connections, and you have to give it a number of how many pending connections is the maximum that you want. Don't worry too much about that 5. It's going to be enough for now. And then, because it's a server that will run forever, you will want an infinite loop. So we have a socket that is now in server mode. It's listening for incoming connections, and we have to accept incoming connections. And in Python, the way you accept incoming connections is you call accept on the socket object. This returns a tuple of a client socket and an address, which will be, again, a tuple of interface port. So we will do some fancy logging. So we got a connection from this address. Fancy. And then I could just handle the request in this server function, but we want to write nice and clean code, so we will actually just pass the client socket to a handler function where we will handle the requests that come in. So let's write a handler function. Again, this will take a socket as its input and has no return. And again, we want to have super duper high performance here, so we will not just handle one request per connection. We will actually allow the clients to reuse their connections. So we will again do an infinite loop, and we will want to receive data from the client. The way you receive data from a client in Python sockets is you call receive on it, or RECV, short for receive. And we'll say we want a maximum of 100 bytes. We're not actually going to use that much, but let's just be sure. So we call this as a request, and this will be a bytes object. But our algorithm takes numbers. So a nice thing about Python bytes objects is if you send it an ASCII number and you just call int on it, it will just give you the correct number that you would expect. So we can just do number is integer request. And then to get the result, we call our algorithm with this number, and then we have to send it back to the client. And to do that, we just call socket send, and this expects a bytes object again, but we will actually terminate it with a new line just so it's easier for the client to handle. So we need to encode this. Fine. We also need a thing to see if the client is done with all their requests. So we'll just say if the request is empty, if not request script, we will close the socket and break the loop. Good. And now, assuming I have not made a typo, believe it or not, these, 20 lines of Python should be a working server. So let's jump over to shell. And I'm going to use a thing called NC a lot during this talk. NC is netcat. You can think of it as cat, but over the network. It's just a very, very, very easy way to talk to a TCP/IP server. So you can just connect to a host port pair. Oh, right, I need to start the server first. My bad. And now we're connected. And so now this expects numbers. So another thing about this talk is we want some audience participation. If somebody from the front row could give me a number. 7. 49. Amazing. And just to make sure that this actually does more than one number per request, if somebody else wants to shout out a number. 0. 42. Fantastic. But I mentioned in the beginning, and I've been repeating this, we want this to be super duper scalable. So we don't just want to handle one client, we want to handle 1 million clients. So let's emulate another client and connect. And if somebody else wants to give me a number, that's going to be tricky. 42, wow. And wow, this is embarrassing. I tried to make it super scalable, but I mean, let's try 42 over here. It just works. It's weird. Well, what's going on? Well, we've just hit the limitations of a single-threaded, single-process server in Python. Because our code in Python, if you write a bunch of code, what happens is Python will run one line after the other, just as you would expect. So what happens is we accept the connection from the client, and we call the handler function, and the handler function is while true. So while the first client is connected, the server code will not run, so it will never accept the second connection. But what we've also seen is that the first client wasn't actually doing anything while I was trying to do the thing with the second client. So it was just sitting there doing nothing, and that's wasted time, wasted resources, and surely we can do something about this. Now Python 3 added a new thing called async await, the keywords async and await, and I hope that they can help us. So let's make this code asynchronous. So I will just make async def, that's how you define async functions. So there we go, we made our server asynchronous and we made our client our handler asynchronous. Wonderful, so let's start our server again and, okay, that's again weird, it just stopped. I mean, it has 2 while true loops in there, but it just stopped. And it gives me this weird warning, runtime warning, coroutine server is never awaited. Yeah, what does this mean? So let's do a little bit Python 101. And first, if we make a function foo, and it prints foo, if we call the function, it prints foo. This is IPython, by the way. But then if we do an async function bar, and we print bar in it, and we call that async function bar, it doesn't print anything, but it returns some strange coroutine object. So let's look at what a coroutine object is. So in IPython, the nice thing you can do is you can write a variable name, then a dot, and then you hit tab, and we'll tell you all the methods and attributes on that object. So you can see there's a close method, there's some CR attributes, which we're going to just ignore for now. And there's going to be a send and a throw. And I've done the homework for you, and I've actually read the documentation on how async await works in Python so that you don't have to read that stuff. So I know that the send method is actually what we're interested in. And we're going to do a weird thing. We're going to call send with none as an argument, hit enter, and 2 interesting things should happen. First of all, at the top there, you see it printed bar. That's what we wanted. Hooray. The second thing is a bit weirder, is a bit stranger. It raised an exception. Specifically a stop iteration exception, which is weird because our coroutine function doesn't have any iterators or anything in it. So again, I've gone to the Python documentation and I read up on this, and this is actually expected. This is just how async functions work. Async functions allow you to suspend the execution of your code and then call send to step to the next step. And then when the function is done, it will raise a stop iteration exception. So very similar to normal iterators in Python. And that's going to become useful in a second. And we are just going to need one more little thing. And that's going to, this is where it gets a little bit weird. But if, say we have a class foo, and that implements a double underscore method await, and inside that double underscore method await method, we yield something, and then we take this class and call it from inside a async function with await. We create an instance and then we call await on it. We use the await keyword on it. Then if we create the coroutine for that function, and we call send on it, it will print bar, so it prints the first print thing here, and then it returns the thing we yield in the double underscore await. So we have a way to suspend the execution of a function, manage when it can step to the next step, and we have a way from inside the function to signal to the thing that is stepping through the function some information. And we're going to use these 2 concepts to our advantage to make our app, our server asynchronous. So the key concept of asynchronous I/O is that I/O can be asynchronous. So while we are waiting for I/O to happen, we can do something else. So we need to find the places in our code that are I/O that could block our code for no reason and where we have an opportunity to do something more interesting. And we actually have 3 places to do that. So we have the receive call, where we wait for data from the client. The client might just be not sending us data, or the connection might be slow. So this is a place where we have to, where we can await our, for data. So we just change this to await async receive. We give it a socket and the number of bytes we want to read. And this is not a function that is defined yet. This is a function we will define in a second. The second point where we can have I/O happening that can block is if we send data to the client. Again, the connection might be slow or some other reason might preventing us from sending data right now. So we will also send this to async send, give it the socket and the data we want to send. And the third step where we will block is if we wait for connections from the client. If there's nobody that's trying to connect to us and we call sock.accept, that will just block until somebody connects to us. So we also change this to async accept, give it the socket. And so let's just do short dummy implementations of this. So async accept takes a socket and returns a tuple of a socket and an address. For now, we'll just leave it like that. So async receive does the same thing, also takes a socket, takes the number of bytes we want to read, and returns bytes. And async send takes a socket, takes some data that we want to send, and it will actually return a number of bytes that it sent, but in our little example here, that's not interesting. So we will have to implement these things. And the other thing that we saw is that async functions by themselves in Python don't execute. You need something to execute those functions. And I'm going to call these asynchronous functions, or rather the asynchronous functions that we called, I'm going to call those tasks because they're tasks that we want to accomplish. So when we call the handler function with the client, this is a task and we need to run it. So we will say add task, that task. And then if we call the server, this is also a task, so we call add task again. And so we will define a function that will add tasks to something, and then we need to run these. So let's see, add task will get a task and return none. And we will just, the task we will just say is a type variable. We don't really care about that too much. It's just a task object. And then run takes no arguments, and again, never returns. So for the tasks, we will do a simple thing. We will just keep a queue of tasks around, or actually a deck. If you're not familiar with decks, they're in the Python standard library collections module. They behave very, very similar to a list. I could use a list here, but decks are just optimized to add to the ends and remove from the ends of the list. And that's all we ever want to do, because what add task does is we just append to the list of tasks. And then in run, we will say while we have tasks, we will get the current task. So from the tasks, we pop left. So we add them at the right side and we pop them from the left side. And then you remember that we can call send on this to actually step it to the next step. So we send none. This could raise a stop iteration exception if the task is done. So we'll wrap that in a try except. And if we get an exception, we will just continue to the next task. So we have a way now to step our coroutines forward, and if you remember, we can use these _await classes to signal out of why we stopped executing. And so in async accept, we want to the task that is trying to accept connections wants to suspend its execution until there is a connection coming in from the client. And the way we'll do this is we will implement a little thing. So we will wait until we can read on the socket, because accepting connections is reading on a socket. And then if we can read on it, we will simply accept. For receive, we will do a similar thing. We'll say we await until we can read on the socket, and then just read on the socket size. And send is almost the same, but we will wait until we can write to the socket, and then write to the socket. And this, we of course have to implement until and await, and I just use these names because it kind of sort of reads like English. And because we use Python 3.7, we can use data classes, which are fantastic. You should use data classes. And the until just takes an action, which is a can object, and it takes a target, which is a socket. And the can is just a enum, that's again standard library. The enum module, you can define enumerations. And we define two options on the enum. One is read and one is write. And because we don't really care about the values, we can use the auto function from the enum module to just define some value there. Fantastic. And now we, of course, need to implement the await in our until class, because that's the thing we are awaiting in our functions. And we will simply yield a tuple of the action that we are waiting for and the target that we're waiting for. So now if we call send on our task with none, it will return a tuple of the action that we want to do and the target that we want to do this action on. So let's get this. And then we need to do something with that information. So if the action is can read, do something. Otherwise, if the action is can write, do something else. Otherwise, just raise an exception because something went horribly wrong. So unexpected action. Great. And now comes the actual part that is the most interesting, is what do we do when we have a task that wants to read on a socket but cannot read on the socket right now, or potentially cannot read on the socket right now? Well, we're going to do something very simple. We will just put it in a little waiting area until we can do something. So we will make two waiting areas. So we will make wait read, which will be a dictionary mapping sockets to tasks. So this is a waiting area for all the tasks that want to read on a socket, but maybe cannot do it right now. And we will also make one for write. It's going to be the same thing. It's going to be a dictionary of socket to tasks mappings. So when we, in our run function, if we get a task that wants to read on a socket, we will just put it into the wait read area with the target as a key, which is a socket, and the task as the value. And we will do the same thing for those who want to write. Great. So now we have a way to run our tasks a little bit until they hit a point where they want to do I/O, but maybe cannot do right now. So we'll take those tasks, put them in a little waiting area over there, and then just keep going to the next task. Now, if we ran this code, we would very quickly run out of tasks, active tasks to run, and everything would end up in the waiting area. So we need to find a way to move things out of the waiting area back into the active task queue. And we also need to change our little loop up here, because now tasks move around between the tasks queue and the waiting areas. So we will keep running while we have anything in the active task queue, or while we have anything in the waiting area, or while we have anything in the write waiting area. And if we don't have any tasks, we need to move the tasks out of the waiting areas into the active queue. And this is the second part in this whole presentation where things will get a little bit magical and where I'm going to be a bit hand-wavy, and I'm just going to say let the kernel or let the operating system do its job. In the Python standard library, there's a module called select. The select module has a function called select. And you can call this function with 3 arguments. And all 3 arguments will be lists of socket or list of file descriptors, to be precise. And the first argument is going to be a list of file descriptors which we would like to read on. So we will give it our sockets that are waiting. The second argument is the list of objects we want to write to. And the third argument we will just conveniently ignore. The return value of this function is again a triple, and it's going to be a list of sockets that we passed into the call as sockets that we want to read on that we can actually read on right now. Second item in the triple will be a list of sockets that we passed in as wanting to write to that we can write to right now. And again, the third element we will conveniently ignore. So we have, we will get a list of sockets we can read from, a list of sockets we can write to, and the third one is nothing. So we will just take all these sockets that can read right now, and we'll move them out of the waiting area back into the active task queue. And we'll do the same thing for those that can write right now and move them back into the active task queue. And now again, assuming I didn't make a mistake, which is a large assumption, this should actually work. So if we again simulate a client and we do 7 again, for example, just to see that it still works. And then if we open a second window and connect and give it 42, we get to 84. And I can do this with as many as you want. It just works. And so this is 99 lines of Python using nothing but the standard library, ignoring the part that actually implements this to implement asynchronous networking. And it's a bit hard to see if you can only see that much of the code at any given time, but I believe this is not completely impossible to understand. And since I think I have a little bit more time, let's just step through what happens in the actual code. So Python will execute and it will hit the thing at the bottom where it says add task server localhost 303030 and then run. Because the server is an asynchronous function, no code in this will execute at the beginning. So it will just go into the tasks queue, and then when we call run, we will hit this run function. So the while any task wait, read, wait, write, we have a task, so let's execute the body. While not tasks, no, we have a task, so skip this. So we get our current task, which is the server function. We call send on it with none, which means now the server function will execute. So it will create a socket, we'll set some options, it will bind, it will listen, it will enter the while true loop, and call async accept with the socket. Async accept will await the until thing with the action read and the target socket, which is our server socket. So this will be the return value in our run function. So action is read, target is the server socket. It will put it in the wait read area with the server socket as the key and the server function as the target, as the task. So we loop back up. While any, we have nothing in the tasks list, but we have something in the waiting area. So let's execute. We do not have any tasks. So we get the inner while loop, and we pass in the server socket. And select will now block for a reasonable amount of time until there will be a connection. And then when we have a connection, the server socket is returned in the can read. We put it back in the active task queue, and then actually immediately pop it out of the task queue again, and continue our server code. So now we are here, we have a client, we have an address, we print this thing, and we add a new task, which is the handler task. And then we loop back to the while true, and we await again accept. We're waiting for connections. So in our run loop, the action is again read, the target is again the server socket. So we put the server task back into the wait read area and continue on top of our loop. Now the handler function is in the task queue, so we take it out. We run the handler function until it's first await, which is async receive. So this time the target is the client socket. The action is still read. So it also goes in the wait read area. And now we have both the server socket and the client socket in the waiting area for reading. And this is where I cannot tell you anymore what's going to happen next. Because now it depends. If the client sends some data first, then we will take the client out first and continue there. If somebody else connects first, then we'll handle that new connection. And so the tasks move into the task queue, and then into these different waiting areas, back into the task queue, back into the waiting area, back into the task queue, back in the waiting area, and do this hop back and forth. But the interesting thing is that we only ever have one current task. So unlike something like multi-threaded programming in Python, you don't have to worry about locking or race conditions or that code magically running at different times. It's still just serial Python code. You can just step through, and just every time you have an await keyword, your current task is going to be suspended for a little while, and something else is going to run. And yes, this is, I see we're running out of time, so this is more or less it. But if anybody has any questions, I would be happy to answer them. I'm going to preempt the first question that we're probably going to have, because every time I gave this talk, people asked, is, am I going to put this code somewhere online that you can have it? And the answer is no, for several reasons. First of all, I don't want anybody to actually use this in production. If you actually want to use asynchronous networking, and I recommend you to do so, please use Async.io or Tornado or Twisted or something else that has been built with production in mind. And the other reason why I don't want to just upload this to the internet for you to download and then go like, okay, now I understand it, is that in my opinion, a way that I try to understand things is by implementing them. And so what I recommend you to do is, when you're back home or maybe on your flight home, to actually try to do what I just did yourself. And it's completely okay if you just have the video running and just type it as you see me typing it. But yeah, the idea is you type it yourself. And if you want some extra homework, you can do this thing, but you're not going to use select.select, but you're going to use something more appropriate to the platform you're using. Select is nice because it will work on Windows, OS X, and Linux. But if you're on Linux, you probably want to use something called epoll. And that is also in the selection module, so you can do select.epoll, read the documentation on epoll to see how it works and try to make it work. If you're on OS X, you want to use select.kq. And if you're on Windows, you want to use select.devpoll. And those all behave slightly different, and you're probably quickly going to realize why those APIs are better than select.select. So yeah, I hope this was somewhat understandable and interesting. And yeah, if you have any questions, feel free. And thank you very much.
Hello? Raise your hand and I'll bring you the mic. I think I saw.
Hi. Congratulations for your talk. It was really interesting. I can see that Async.io in Python builds upon generator functions. Is that correct? Is there something in Python which have similarities with promises in JavaScript?
Yes. If you use Async.io or Tornado or Twisted, they all have something similar to a promise. In the Python world, this is usually called a feature.
Okay.
But yes.
Okay. Thank you.
Next.
Congratulations on this and the guts to actually pull this off in life. So
thank you.
I wanted to ask, what's the main advantage of using classes for until, instead of using a direct function?
Yeah. So yeah, that's a good question. Like, why do we need this weird function class and this underscore await? And the reason for that is this is how the protocol of like how the Python implementation of async await requires you to do this. So if you're going to write your own application code, like your actual business logic and things like that, you would rarely or never actually write a double underscore await function method. That is really only for when you try to implement this system, you have to, at some point, do this method to do the very low level signaling between your run function, or it's called an event loop, and your tasks. So yeah, usually you would only write things like this, where you have an async def, and then you await things, and you don't really have to care about if it's going to be another async def function or a class with a double underscore await in it.
Yeah, thank you. It was a wild ride, I guess. My question is, you said we should not use this in production, I believe you. What's the thing that will bring this down in a production environment, and what do the more mature frameworks do to mitigate this?
Yes, so there's several things. First of all, this is very incomplete, and this doesn't handle threats at all. So if you want to try to mix this with threats, you're going to be very sad very quickly. The second problem is that, yeah, again, that select. Select is great for portability, and it's just the easiest API you can use to showcase how this works. But it's also really terrible because you have to pass in the whole list of objects you want to listen on every single time you call it. And so if you actually run this in production, you have like 10,000 connections, you pass 10,000 file objects between user space and kernel space all the time, and that's just incredibly inefficient. So you would want to use something like epoll, where you actually have the kernel manage the list of things you're interested in. And on Windows, it's IOCTL, and on OS X, it's KQ. But yeah, they're all working with the idea of not having to pass massive amounts of data back and forth all the time. And the other problem with this is this doesn't handle error handling at all. If there's an exception anywhere in this, it will just break horribly. And these frameworks like Async.io or Tornado Twisted, they will actually not completely break if you have an exception, which is a nice thing.
So before you told about the futures.
Yes.
So probably the until class could be a future, because you could wait on that.
Right. Yes, but usually when people say a promise or a feature, they mean an object that they can have, like a method to add callbacks to, and then a method to set the result to. That's how I understand people thinking about features and promises.
Anyway, if you just wait on that and the rest of nothing, when this is ready, you go on.
Not quite. You have to handle it a little bit different because it has to be handled in the run function, basically.
Okay. Second to last question, and one more question after this, and then we'll wrap up.
All right.
Yeah, thank you for your great talk.
Thank you.
This is inspiring life coding. I actually tried to do the same thing myself, and I failed horribly. So I know it's not easy. But now, having seen that it works and it can work, I would immediately go on to the next more complicated thing, which is basically forking off intensive tasks into a thread and trying to implement that myself to understand how it actually works. It's completely possible in Python, I know that,
Yes.
but I don't understand how it works. So what would be your
So,
guarding advice how to proceed then?
So if I had 30 more minutes, I could have implemented threads probably. But yes, it is a bit weird, and it behaves in a weird, unexpected ways. So the TLDR for how to do threading in Async.io is you create something called a socket pair. That's a function in the socket module. You can create a socket pair. You get two sockets that are connected to each other. You hand one to your thread, and you keep one in your main thread. And then you basically wait until there's action happening on that socket object, and you use that socket to signal when your thread is done. That is the very, very short version of it, and that's how you would do it. And yeah, just like you said, you tried to do this and you failed. That's completely okay. This is not the first time I write this code. I've written this code like hundreds of times to prepare for this. The first time I did it, I didn't do it in 30 minutes. So yeah, don't be too intimidated by me standing here doing it in 30 minutes while I talk. That's just, I practice this a lot. So don't be discouraged if this takes you a couple of hours or whatever to do. That's expected.
Okay, I think time is short, so let's say thank you to Jonas.